the more fun and interesting bit of introducing and welcoming our speaker. So our speaker is, so the talk is Through Time and Space, 350 Years of the Royal Observatory Greenwich. And our speaker is Catherine Muller. So let's give her a big warm welcome as we welcome her to the stage.
Hi, everyone. Thank you, Adam, for that introduction, and thank you, everyone, for coming. As Adam said, my name is Catherine. I work on the astronomy education team at the Royal Observatory, and I'm really excited to speak to you all about the place that I work today. One thing to say, as you can tell, we want to try and fit in 350 years of history into what's essentially 45 minutes, which is quite a task. So many people have worked at the observatory doing so many different things with so many different instruments. So if I don't mention your favorite astronomer or your favorite telescope or anything like that, you will have to forgive me, because yes, there are so many different stories that we could tell, but I hope that I've managed to pick out some of the best bits, really. So we're going to start off by sort of setting the scene with where we were in pre-1675, the year the observatory was founded. Firstly, by thinking sort of where we were in the field of science and astronomy. In the 1600s were actually a pretty exciting time in that field, largely because of the invention of the telescope. Now, there is, of course, lots of debate about where the first telescope came from. There was someone called Hans Lippershey in 1608 who created an instrument with lenses in it that was used to see things that are far away better. But definitely one of the most famous people that used it was Galileo. And he made lots of fantastic discoveries, the phases of Venus, but perhaps most sort of groundbreakingly was the discovery of 4 moons around Jupiter called Io, Callisto, Ganymede, and Europa. This was absolutely huge because prior to this, a lot of people still believed that the Earth was at the center of the solar system and the universe. So this was the sort of first definitive proof that that really wasn't the case. So this really sort of shook things up, and there was lots of other things that were going on with the help of the telescope. Suddenly you're able to see sunspots on the sun in more detail. Those drawings on the bottom left were done by a British astronomer called Thomas Harriot. The telescope helped us study the moon in more detail. This is a drawing of the moon by another really famous astronomer called Johannes Hevelius. So it was a really exciting time because for the first time, despite the fact that humans have been looking into space and looking at the stars for thousands of years, we were able to peer a little bit deeper. So that was all going on, and that was great. There was some other stuff going on as well in the 1600s. Britain and other nations depended on the sea for trade and for empire, which of course meant sailors on ships. Now, this is great, but if you want to try and work out where you are in the world, that's essentially what you need to do. Where you are on your boat, you need to work out your position, which requires 2 things, latitude and longitude. Finding latitude is relatively straightforward. All you need to do at night, for example, if you're in the northern hemisphere, look up to the stars, locate the pole star, Polaris, also known as the North Star, and find the angle between Polaris and the horizon. You've got your latitude, super useful. That's how far north or south you are of the equator. Longitude is a little bit trickier. It was more of a problem. There were sort of ways that you could think about it. So if you imagine planet Earth as kind of like one great big Terry's chocolate orange, and you split that chocolate orange into 24 segments, each one representing sort of an hour, so with a day being 24 hours long. The sort of difference between each segment would be 15 degrees apart in longitude. And so if you have a time difference of an hour, that's about 15 degrees you've moved sort of east or west, theoretically. Trying to put this in practice was a little bit trickier because the main problem at the time is there were clocks. Clocks did exist, but they weren't very good at keeping time at sea with their pendulums. They'd sort of get stuck and not work properly. So it was really hard to find your longitude, which wasn't great. It meant there was loss of ships, loss of life, lots of money, not ideal. And the king at the time, King Charles, wanted to try and find a way to sort of solve this problem. And he'd heard rumors from the observatory in Paris, which was founded in 1667, that an astronomer there had worked out a way to find your longitude using the position of the moon relative to the stars. So King Charles, he was interested in science, he wanted to find out more about this. He asked some people at the Royal Society to sort of think it over, tell them if they thought it was possible. They said, yeah, you know, we think this will be possible. The trouble is we don't have enough astronomical data to be able to sort of confirm or deny or essentially make it easy for people to do. So that inspired King Charles to found the Royal Observatory. So it was founded specifically for rectifying the tables of the motions of the heavens and the places of the fixed stars so as to find the so much desired longitude of places for the perfecting of the art of navigation. That was the observatory's sort of original purpose. And the person he hired to do it was this man just here, John Flamsteed. He was hired as the Royal Observatory's first astronomical observator, which nowadays we would call the first Astronomer Royal. And the observatory was built on the site of the old Greenwich Castle in Greenwich, in what's now Greenwich Park. And the reason for this, there were a couple of reasons. Firstly, the land was already owned by the king, so that meant it was essentially free. It was up a hill, so you had quite a nice view of the sky and the stars. It was sort of at that time pretty far out from the centre of London, so there was less sort of pollution and smog, and it also had really great river access. So it was a good place to sort of start. The observatory was designed by Christopher Wren, and whilst it was being built, John Flamsteed actually worked out of the Tower of London, so that's where he was. And the foundation stone, as I say, was laid in 1675, so 350 years ago this August. The room that they designed to give Flamsteed as his observing room was this room just here. On the left, you can see an image of it in 1712. This is how it looks today. It's pretty much the exact same. This room is really nice. It's really big. Ceilings are really tall. It's got nice windows. You can look out the windows. It's got a nice view of London. It's a really nice room. It is not a useful room in any way for making any sort of astronomical observations. And the reason for that is because all of these lovely windows, none of them are north-south facing. So not great for observing. When you want to build a star map, essentially what a lot of the astronomers would do is they would have their telescopes in a fixed direction. So that just sort of made it a little bit easier. And then track what time each star crossed due south or due north. And that's the sort of easiest way to build up a big picture of where all the stars would be relative to each other. So that's why it was kind of important to have a north-south facing window. This building didn't do that. We don't entirely know why. Maybe it was because they built on old foundations. Maybe it's because they liked the lovely facade of the building facing down the hill. But either way, that meant that John Flamsteed and some of the earlier astronomers that worked there couldn't observe from this room. They observed from telescopes in wells and in sheds, which is not ideal. And if you take a look at this picture here again, just out the back, just here, you can see a sort of mast structure. That was the first mast telescope that was erected at the Royal Observatory 1 year after it was opened in 1676. So they were making use of all sorts of different things until eventually a sort of designated building for observing was created. So what was Flamsteed actually getting up to? Well, as I say, he was trying to make incredibly accurate star maps. And here are two of those maps from Historia Coelestis Britannica. This was published in 1725, 6 years after Flamsteed died. Flamsteed worked at the observatory for over 40 years. And in that time, he was not 100% fully happy with the maps he had created. He was an absolute perfectionist. He wanted the over 2,900 stars that he had documented to be perfectly positioned. And this actually got him in a little bit of trouble with another very famous scientist at the time, Sir Isaac Newton. Isaac Newton, again, very famous, doing his own sort of physicsy, sciencey work. He really wanted to use Flamsteed's data, all of the information he'd collated. But because Flamsteed was such a perfectionist, he was like, no, absolutely not. They're not ready yet. You can have them when they're perfect. Eventually, Isaac Newton became the president of the Royal Society, which is what sort of overlooked a lot of the work of the observatory at the time. So, using his position of power, Newton and his assistant Edmund Halley, who would later, by the way, replace Flamsteed as the second Astronomer Royal, they had managed to obtain a sealed copy of Flamsteed's work in progress and published, without Flamsteed's consent, 400 copies of his work. As you might expect, Flamsteed was absolutely fuming. He was raging. So what he did was he collected up, well, he petitioned the Crown to have 300 of the copies that were printed sent to him. They were sent to him, and he gathered them all up in a pile, put them in the courtyard of the Royal Observatory, and set them all on fire so as to avoid anyone using his potentially slightly imperfect works. So he took his work very seriously, and as I say, managed to document lots and lots of stars. Now, the interesting thing I think about looking at these sort of star charts and maps from hundreds of years ago is, of course, it wasn't until 1930 that astronomers around the world decided on a sort of universal set of constellations that they would refer to when doing astronomy. Before that, different civilizations around the world would look up into the sky and see whatever they like. So depending where you were, you would spot different things in the sky. It also meant that before that, astronomers could sort of do what they want. If they decided they wanted a new constellation, they could just put it in their work, and then some people might use it, some people might not, until it sort of fell out of fashion. So it means that when we look at these maps, there are a couple of fun little things that you can pick out that we don't use anymore in astronomy. The first one is just here. We can zoom in a little bit. This is the constellation of Cerberus, which represented a three-headed snake being held by the constellation of Hercules. Nowadays, this is not a constellation at all, so you'll never hear anyone talking about this constellation. Those stars simply form part of Hercules. So Flamsteed included this, but if you take a look at this image to the left, from 1825, a couple hundred years later, you'll notice there's a second constellation by Cerberus called Ramus Conifer, which is a branch. So another sort of different constellation that sort of fell in and fell out of fashion. Both of those no longer exist anymore. So I think it's nice to sort of see what they were looking at back then. Another example is this outrageously large constellation called Argo Navis. This constellation was absolutely huge. It was one of Ptolemy's original 48 constellations, which is what a lot of these constellations still are. And as I say, it was absolutely massive. It had 160 visible stars in it, and it's about a third bigger than the biggest constellation that we have now, right? So this thing is very big. So essentially, what was proposed was that it gets split up. So they've split up the big boat into a couple of different constellations here that represent different parts of the ship. So the sails, the keel, and the poop deck. You might be able to see the ship a little bit better on the side monitors there. So that constellation just doesn't exist anymore either, but it was a pretty famous, pretty one that was used at the time. One of the other things that Flamsteed is kind of famous for spotting was in the constellation of Taurus, the bull. One of the stars he noticed was this one just here. Now I say star, this was actually not a star. He called it 35 Tauri. What it actually is the first recorded observation of the planet Uranus. So people might have spotted it before. He was the first person to write it down and include it in a star map. He is not credited with discovering Uranus because he did not know that it was a planet. He just thought it was another star. So Uranus was officially discovered as by William Herschel in 1781. And it was only when you look back at these maps that you see, oh, Flamsteed did actually find it, but he just called it a star. It doesn't count. So yeah, Flamsteed did lots and lots of work. That was just some of it, really. But back to sort of the problem at hand of time and longitude. This subject is dense. There's lots and lots of different things, lots of different history, lots of things at play to try and solve this whole problem. But we'll sort of start off in 1714 when the Longitude Act was passed. This was an act of parliament that offered someone, a company, anything like that, £20,000 to find the solution to the problem of accurately finding navigation at sea. Now, £20,000, obviously it's a lot of money today. It was more sort of money back then, but to put it into even more context, John Flamsteed was being paid £100 per year to do this work. So it really, really was a massive amount of money. Now, obviously this inspired lots and lots of different people with lots and lots of different theories to come forward and try and claim this cash. Some of them are potentially a little bit more sensible than others. One of the most famous stories involved something called the powder of sympathy. It's a slightly distressing tale which involves someone using a knife to wound a dog, taking that dog, putting it on a boat, sending that boat out to sea, someone back on land, grabbing the same knife that they used to wound the dog and plunging it into a bowl of powder, which they called the powder of sympathy. The theory was when they did that on land, they'd do it at midday. And when that happened, the dog on the boat would howl out. And that would mean it was midday. So this idea, unfortunately, well, maybe not unfortunately, it did not receive any money. So there were, examples like that. Other examples were using Jupiter's moons as a sort of clock, using their orbital periods and positions to sort of work out what time it was. So again, try and find out how far you'd moved, east or west. Theoretically, it works, and it does work, but it was potentially a little bit too complicated for people to try and achieve at sea. So yeah, lots and lots of different ideas. Where it really sort of started to come together was with a man called John Harrison, who was a carpenter by trade, a self-taught clockmaker, and he worked in Barrow upon Humber. And in 1735, he presented the board with his first timekeeper, H1, Harrison's first clock. This was, I guess, different to normal pendulum clocks. At the time, it had two different sort of balances. I'm not a clock person, so you'll have to forgive me. And that sort of helped keep the pendulum ticking at the right sort of rate. So the board ordered a trial. They put this on a boat on a trip to Lisbon. It worked, pretty well, better than a lot of the other things at the time. But the board decided that it didn't keep time quite well enough to be, worthy of the prize. So as you can see, decades passed whilst Harrison and his son were working to try and make these clocks. There was an H2 and an H3 until eventually in 1959 he presented the board with H4, a much sort of smaller, more compact timepiece. This got sent on another voyage out to Jamaica. And by this point, John Harrison, the original Harrison, was getting pretty old. So his son went on the voyage instead and used this timepiece to accurately sort of work out their longitude and predict that they were going to hit land at Madeira sooner than the captain thought they were going to, which was good news. The captain was really, really impressed and wanted another copy of this timekeeper. So they went back to the board and the board said, listen, here's what we will do. We will give you £10,000 sort of now, and £10,000 once you can prove, or once you have made lots and lots of these, once you've proved it's sort of not just a one-off. There was actually sort of a lot more that went down between Harrison and the board. They were trying to get money quite a lot. The board kept refusing. It was sort of a whole thing. But John Harrison is credited with being the person that solved the longitude problem, which is great. That is not where it ended, though. There was lots of other sort of stuff going on in the world of time and longitude. The first nautical almanac was published in the year 1767 by the 5th Astronomer Royal, Neville Maskelyne. Again, this was meant to help navigation. It contained a set of tables showing the position of the moon's angular position related to nearby bright stars, and how that was, or when that was, in Greenwich time. Sailors would then have to do bunch of calculations, correct for parallax and refraction, blah, 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 and sort of use that to work out their longitude. So it was a different way of doing it. And more sailors did sort of start using it, as well as chronometers, these sort of marine timekeepers that were gradually, very gradually, becoming more and more used. So that's great. Fast forward quite a few years, and at the Royal Observatory, they installed the red time ball. If you've ever been to the observatory or seen the observatory from Greenwich or the river, on top of Flamsteed House, that building with the octagon room, there is a bright red ball. This was one of the first public time signals. What it does every single day, unless it's windy, is that ball rises to halfway up the mast at 12:55, at 12:58, rises all the way to the top, and at 1 p.m. it falls down, which means if you're looking at it, you have a chronometer or something, or you want to know what time it is, that will tell you once and for all that it is 1 p.m. And ever since Flamsteed, the observatory made a point of having really excellent clocks on site. Flamsteed really wanted the best timekeepers, the best pendulum clocks on site. So that's how they were able to keep time really, really accurately. Eventually, in 1852, a new clock was installed at the Royal Observatory called the Shepherd Gate Clock. This was the first clock that would publicly show Greenwich Mean Time, the time that the astronomers were using at Greenwich. This was also very useful because in the 1850s and 60s, the railroad started to expand. So people really started to be like, we need to all be on the same time here, because one town or another city all having or using different times was not sort of working anymore. We needed to sort of coordinate. So the Royal Observatory was sending out time signals to places like Edinburgh, Dublin, Belfast, via telegraph wire. And in 1880, Greenwich Mean Time became the official legal standard time for the UK. Around the world, everyone was sort of coming to the same conclusions. You know, it would be great if we all knew what time we were all working on. So a couple of different people from different observatories, different places around the world came to a conference in Washington, D.C. in 1884 to decide where should be the prime meridian, longitude 0 degrees, where everything would be measured east or west from. Greenwich was chosen, and it was chosen for a couple of reasons. Obviously, it was used in the UK. It was also used in the United States. They based their clocks most of the time off Greenwich Mean Time. 72% of ships that were being used at the time for trade and commerce were also using either the almanac chronometers that were based on Greenwich Mean Time. So it just sort of made the most sense for the most people. So Greenwich was chosen. Happy days. And what was chosen to be the meridian line was, as I mentioned, when astronomers like to do their observing, they like to do it on sort of facing north or facing south. So if you imagine that line cutting down onto the floor, it was done at the meridian line of the Astronomer Royal at the time, who was George Airy. This is his telescope called the Transit Circle. It's quite a cool telescope. It's still there at the observatory. To use it, you've got to sort of open the roof of the building, just like that. And so the meridian line was lined up with the crosshairs of his telescope. All the different Astronomers Royal prior to that would have their own meridians, because there's this building at the observatory, and the Astronomer Royal would come in, they'd build a telescope, they'd live, then the next one would come in, and they'd be like, I have a better telescope than that really, couldn't I? So they'd build a new telescope, just sort of to the left of it, and then define where that new telescope was as their meridian line. So this one ended up being the one that became the historic prime meridian. Now, I say prime meridian, historic prime meridian, because this is the line, the famous line on the courtyard at the Royal Observatory. This is not the actual prime meridian anymore. The actual prime meridian, since 1984, has run about 100 meters to the east of the historic prime meridian. The reason for that is because as GPS became more popular, a bunch of scientists basically sort of sat down and accounted for some different things with the Earth and its gravity and blah, blah, blah. And they were like, oh, it just makes more sense to put it 100 meters to the east. There is a sign at the Royal Observatory, don't worry, that says this is not the actual prime meridian anymore. If you stand on it and you get your phone out, you will be sad because it doesn't say 0 degrees longitude. And if you look very closely, you might be able to tell that the actual prime meridian does not run through the site of the observatory at all, which means we cannot put anything in the park, because we don't own the park, to say where it actually is. So if you want to find it, sort of good luck. It's like a bit of a treasure hunt to go and find the actual prime meridian out there in the park using your phone with GPS. But it is there. So that was an absolutely rapid overview of the time and longitude aspect of the Royal Observatory. But of course, there was lots and lots of other astronomy going on at the time. The Astronomers Royal weren't the only people that worked there. And one of the other especially famous telescopes at the Royal Observatory is this one here, called the Great Equatorial Telescope, or the GET. This telescope is mostly interesting because it is absolutely massive. It is the largest of its kind in the UK. It's a refractive telescope, which means it uses lenses as opposed to mirrors, which more modern day telescopes use. As I say, it's really big, 28 feet long. The lenses are 28 inches across. And this is annoying for a lot of reasons. And it was not the first telescope to be built sort of in this dome. There was one before, and it was smaller. And when they got rid of it, the order of events afterwards was the astronomers went to the Admiralty, who was looking after the observatory at the time in the 1890s, and they said, please, can we have a new telescope, please? And they said, yeah, okay, you can have one. And then they went back and they said, can we actually please have some more money, because the dome that currently already exists is not big enough to fit the telescope. And the Admiralty sort of reluctantly agreed and gave them the money to build this dome. Whether or not the astronomers knew that that was going to be the case, your guess is as good as mine. But so they built a dome, but they ended up building this sort of funny onion-shaped dome. This is the telescope in the 1890s. On the left, you can see Edward Walter Maunder using it. Again, its size means a lot of different things. Firstly, if you take a close look, it might not be immediately obvious, but the telescope is not one huge cylinder. It's sort of cylindrical at the ends, and in the middle it's a square, essentially it's flat. And that is because they reused the mount of the original telescope, so it didn't fit in properly, so they sort of had to squish it in. It also means that when you operate the telescope, and you can still operate it, it's completely operational, you have to be really, really careful moving this thing around, because it's really heavy. So when you push it one way or the other, it picks up momentum quite quickly. If you swing it too far one way or the other, it will crash into the dome. It is just not big enough. And the dome at the time was very cleverly made out of paper mache, which meant it wasn't going to survive any sort of impact. Final thing is, if you take a look at this astronomer just here, he is observing lying on a grubby mattress. The old telescope was small enough that you could have a lovely chair and be very civilized when you did your observing at the Royal Observatory. But with this ridiculously, comically large telescope, you couldn't do that anymore. The astronomers had to lie on a mattress. So it wasn't super ideal. When World War II came around, you might be wondering if the paper mache dome survived the war. It did not. There was a bomb that went off in Greenwich Park, destroyed the dome. The telescope had been taken away from the Royal Observatory over to Hurstmonceux, where it was until the 1990s, actually. And the dome did end up getting replaced. Now it's made with fiberglass. You still don't really want to whack it with the telescope. But as I say, the telescope has now returned to the Royal Observatory, and it is completely functional. It works absolutely fine. It was mainly used for studying binary stars. These are two stars that orbit around one another. And the astronomers at the observatory would observe about 600 of these a year. And this was a really sort of useful, interesting thing to be able to do, because all you needed was two pieces of information that you could get relatively easily with your telescope. You needed to work out the orbital period of the star system, so how long it took the stars to orbit around each other, and you needed to work out how far away they were from each other. And from that, you could use Kepler's third law to determine the mass of the star system. So if you've ever wondered how we work out the masses of stars, this is what we do. And if you're then wondering about, I say we, I don't do that. If you're then wondering about how stars that aren't in binary systems, you work out their mass, through all of this work, scientists were able to see that there's a relationship between the mass of the stars and their luminosity, so how bright they are. That's great, because that means when we look at stars that aren't binary stars, if you're able to work out how bright they are, you can then work out how massive they are as well. So it's pretty useful to do if you care about measuring the mass of stars. On the right, this is an image of Albireo captured by the Great Equatorial Telescope. For a really long time, it was thought to be a binary star. Turns out people might have been wrong for a long time. It might actually just be an optical double where they look really close together, but actually aren't related at all. But that's okay. As I say, telescopes still used today, lots and lots of other things we can capture with it. A transit of planet Mercury passing in front of the sun in 2016, we get nice views of the moon, or even slightly further out into space. We have an example of a planetary nebula here called the Blue Snowball. So that was one of the things that was going on at the time, and you might have remembered a few slides ago when I mentioned someone called Edward Maunder, or Walter Maunder. He had a wife, Annie Maunder. Now, Annie Maunder was an incredible woman. She was not just Edward Walter Maunder's wife. She was educated at Cambridge, and she was an incredible scientist, dubbed a lady computer, but she did some absolutely exceptional work regarding the sun at the Royal Observatory, where she started in 1891. She's really sort of one of our highlights. We love talking about Annie Maunder. She used a telescope just like this, a photoheliograph, to take pictures of the sun. She traveled. She didn't just stay at the observatory. This image just here of the sun's corona, the outer atmosphere of the sun, was taken by Annie Maunder in Mauritius with a telescope similar to that. And the other thing that she did was take a daily photograph of the sun to capture things called sunspots, which are these dark, cooler patches on the surface of the sun. And if you do that every single day, you can track the position of all of these sunspots. And when you put them on a diagram, just like this, which has sort of the year, so the time, and then the latitude, you end up with something like this, which is called a butterfly diagram because of its shape. We get these lovely sort of butterflies appearing. This is Maunder's original butterfly diagram from 1904. This is not that, but this might be a sort of slightly easier way of representing sunspots on the sun. You can sort of imagine them pictured there. This is later data from 1974 to almost now. So it shows really, really clearly the regular 11-year cycle that sunspots on the sun go through. So every 11 years, there is a maximum of sunspots, and then they sort of die out a bit, and then it comes back. Sunspots are associated with sort of greater magnetic activity at the sun, which means often when you're in a solar maximum, when there's lots and lots of sunspots, you might expect to see sort of more of the northern lights, more of the aurora where you are. So right now, sort of 2024 to 2026 is expected to be a period of maximum solar activity, which is why you might have noticed lots of people at further south latitudes are seeing the northern lights for the first time, or you might be seeing them slightly more at higher latitudes. So Annie Maunder was really, really sort of instrumental in creating and popularizing this diagram, which is now very widely used and is a fantastic tool for showing data and sunspots on the sun. I said that we really loved her. We absolutely do. We're huge fans at the Royal Observatory, so much so that we have named our most modern, up-to-date suite of telescopes after her. This is called the Annie Maunder Astrographic Telescope. It was installed in 2018. It's a suite of 4 telescopes that do a whole bunch of different things, including take pictures, taking pictures like this. You might be able to spot a little bit more detail in that one on the right on the screens. So on the left, we have a solar prominence, so a sort of loop of plasma being ejected from the sun on the left. You can also see lots and lots of detail in the sun's surface called granulation, which is where you have convection cells of plasma rising from the sun's interior. And then on the right, we have an image of something called the Veil Nebula. This is the leftovers. In astronomy, lots of different things get called nebulas. But this one in particular is the leftovers of a star that went supernova in the constellation of Cygnus about 10 to 20,000 years ago. This would have been about 1,500 light years away from planet Earth. And the reason I've chosen this picture instead of a picture of the moon or something like that is because this nebula was actually only discovered in the year 1784, again by William Herschel, which means when John Flamsteed was working at the Royal Observatory, and some of the Astronomers Royal subsequently, they wouldn't have even known that this thing existed. They wouldn't have had a clue about it. And nowadays, some of my colleagues who are not the Astronomer Royal, but do work at the Observatory Greenwich, have been able to use the telescopes on site to capture incredibly detailed images like this of something that 350 years ago we never even knew existed, which I think is pretty impressive. And that sort of leads me on to the current Astronomer Royal, Professor Michelle Doherty, our sixth Astronomer Royal. She was appointed earlier this year. The Astronomer Royals now don't really have anything to do with the observatory. They don't really work for the king anymore. It's more of a sort of honorary title. And I'm not going to talk too much about Michelle because she's alive and she does amazing work. She can absolutely speak for herself. But one thing I did want to sort of bring up was the work that she does do. She is the principal investigator on one of the instruments on the JUICE spacecraft, which is the Jupiter Icy Moons Explorer. This is a European Space Agency satellite, which is currently on its way to planet Jupiter to explore the moons of Jupiter, the icy moons of Jupiter that were discovered by Galileo over 350 years ago. So 350 years ago, big news at the time, something that the Royal Astronomer would have been interested in and known a lot about would have been those moons of Jupiter, just the fact that they existed. But now, in those 350 years, I think it really shows just how far we've come in terms of our astronomical knowledge, that we are, the Royal Astronomer now is working on something in space, getting that close to the moons, which I think is fantastic and brings us quite nicely to today. Royal Observatory is a museum. We don't have any sort of active research going on at the moment. We have the telescopes, which some of my colleagues like to use and take nice pictures. But yes, this is where we are at the moment. We're currently undergoing a nice big refurbishment, so it's going to get even cooler in a few years. So that was 350 years of the Royal Observatory, very, very speedily. Thank you very much for listening. That is the end of my talk. I guess if anyone has any questions, now will be the time to take them. Thank you, everyone. Thank you.
Well, if anyone's got to run, any questions, please put your hands up. Please your hand.
Hi, I know there's another observatory in Mill Hill, University College or King's College. Are there any others around London apart from this one as well?
That's a good question. I don't know for sure. I know various different universities around the country have their own sort of telescopes and mini domes that they call observatories. The one in Greenwich is definitely the main one because it has been sort of historically. As for whether or not there are lots of other different ones tucked around, whether you consider a telescope in a university dome or something like that an observatory, I think is sort of up to them. So I don't know for sure, but there aren't any other sort of major significant ones like the observatory.
Over here at the back. Hi, thank you for your presentation. I was just wondering, when we had that dramatic aurora display last year or the year before, if the Royal Observatory were able to capture any images, and also if you recommend that if something like that happens again, if we should make our way to Greenwich Park to observe.
That's a
display.
good question. To answer the second part of your question straight off, no, I would not recommend making a special trip to the observatory, largely because now it is in the center of London. It's right opposite Canary Wharf. There is lots of light pollution in the area. The park itself is quite dark. Unfortunately, in the winter though, they close the park quite early. So in winter time, it closes at 6 p.m. So you're not able to access the park that late at night, when you might be able to sort of spot them. In terms of the first part of your question, I went on a tangent. Can you just remind me?
Just wondering if any of the telescopes were able to that dramatic display. I think it was it 2 years ago or last year?
Yeah, that's a good question. Unfortunately, sort of not is the short answer. And one of the main reasons for that is because auroral displays are incredibly hard to predict. Being able to see the aurora at a latitude as low as London is pretty tricky and pretty rare anyway. So to be able to sort of predict that wouldn't really come easily. So there's no way we would sort of be able to prepare for having someone on site and pointing it in the right direction and sort of picking it up. I know when we do hear about things like this, our team get very excited and we send each other lots of WhatsApp messages trying to find if we can see them. But no, unfortunately, due to the nature of the aurora, it's not super easy. It'd be very cool if we could do, but it's not, unfortunately, something I would do. I'm sorry.
Thank you.
Hi, thank you. You showed the pictures of the new astrographics telescope and some very impressive images. Does that have a science function, or how is that put to use today?
Yeah, that's a good question. It's something that one of our sort of teams at the observatory is trying really hard to work on. I know most recently, some of my colleagues that were working on it used it in a sort of citizen science project to look at exoplanets, which are planets orbiting stars that aren't the sun. So they were able to point the telescope at a different star and try and capture transit, so the exoplanet traveling in front of that star and blocking out some of its light. So that's sort of the most recent example of them sort of trying to do science. But really, because the telescope was installed in 2018, it took a bit of time to get to grips with, learn how it's working. Pandemic, obviously, I don't need to explain the pandemic to you guys. It's something, we had to redo the dome, that we are trying to sort of actively sort of do more with while we can, before the site closes temporarily for renovation. So looking at that exoplanet is an example of something I think my colleagues would probably like to try to do more of. I hope they don't mind me saying that. But yes, sort of slowly but surely, we would like to try and do that. I hope that answers your question.
Was there ever any manufacturing done on site in terms of things like, say, glass or mirrors, telescopes and instruments, or was that brought in from elsewhere?
That's a good question. As far as I'm aware, there sort of wasn't really any. They would have external people sort of build the telescopes, like crafts people and things like that, to provide them. So as far as I'm aware, there wasn't any sort of major things, but I might be wrong because I don't know every single nuance of the observatory.
We've got a few questions online. So one person wants to know if we could have any more details or factors that cause the prime meridian to move.
That is a good question. And I guess sort of the truth is, it was decided, and I don't know enough about GPS systems, because when that, I guess, system was sort of up and running, they were able to factor in more of sort of the Earth as a perfectly, or as a not perfectly spherical body, which something to do with perturbations and gravity. I'll be honest, I don't fully understand it. Meant that a collection of scientists decided that it might be better 100 meters to the east. I'm not entirely sure the reason, but it's something to do with the fact that the Earth isn't perfect and the coordinates are slightly off or slightly different.
And we've got another question that's, if Flamsteed ever thought his results were perfect, what and where is the final map?
That's a good question. So Flamsteed's widow, she was the person who published both the book that I took those star maps from in 1725 and a second collection a couple of years later. So as far as I'm aware, those things are sort of, they were edited by Margaret, his widow, and those were sort of the bulk of Flamsteed's work, sort of the best bits of it, right? So they were published without Flamsteed knowing about it. So one would assume that that was sort of the best that he sort of had to offer at the time. His wife, who was picking through it. Hope that answers it.
Hey, so with the current closure of the planetarium observatory and the upcoming closure of the site itself with the renovation, could you tell us a little bit more about the First Light project and what that entails for the future of the observatory?
Yeah, sure, absolutely. So the First Light project, as it's called, it's a good question, is an absolutely massive project taking place at the Royal Observatory, funded by the National Lottery Heritage Fund. The project involves sort of every single aspect of the site, from accessibility to science communication. So one of the main problems with the observatory is that it is an incredibly old building, and as such is not very accessible for members of the public as a museum. To get up to the Great Equatorial Telescope, for example, you have to traverse an incredibly narrow, rickety spiral staircase, which just is not suitable for everyone and for making science accessible. So that's going to change. The galleries in what we call the North site, the historic site, are all going to be redone. They're going to be rejuvenated. The landscaping of the site is going to change. They're going to add a new entrance pavilion. We're going to add, so the north site of the planetarium, the historic site where Flamsteed House is, that the museum content on it right now is currently very heavily based on sort of the clocks and the timekeeping and the longitude aspect of it. At the moment, where we currently, or at the moment, there is nothing. There's no sort of astronomy galleries or any content to do with astronomy separate from clocks and longitude anywhere on site. So that's something that's being developed. They'll be opening new galleries in the same building where the planetarium is. And alongside that, there's going to be lots more programming for the public, for schools as well. So it is very, very exciting. The site is tentatively scheduled to reopen in 2028. The north side of it is still open. So at the moment, our team has moved down to the National Maritime Museum. So we're sort of in a transitional phase. Sorry, this is a really long answer to quite a short question, where hopefully there'll be some new space content coming out of the National Maritime Museum too soon, where our team is. But 2028 is going to be really jazzy. This is your question. That was a lot of words. Thank you.
I've got a question on those constellation maps.
Yeah.
It feels like they were drawn quite artistically for someone who was so focused on getting it exactly right. Was that just how they were drawn back then, or the interpreting?
So all of those drawings, they were not drawn by Flamsteed. The person who did draw them, the man's name escapes my mind, but he would have plotted the stars, and there was a separate individual who constructed all the drawings, essentially. So it was sort of a separate thing. Yeah.
Hi. In terms of Flamsteed's wife, was she an astronomer in her own right, or did she have collaboration from others when she published the maps?
That's a very good question. I really should know the answer to that explicitly. The truth is I don't know 100% for sure. I know she edited a lot of his work before it was published, which implies that she had a certain amount of knowledge about the topic, but I don't actually know for sure, and I should, what she sort of did in her own right, fortunately. Yeah, but she must have had some sort of knowledge somewhere.
So this is another Flamsteed question. How are the charts made? How do you get the data for the Southern Hemisphere maps?
Yeah, that's a good question. So Flamsteed's maps did not go all the way into the Southern Hemisphere. They were mostly based in the Northern Hemisphere. So yeah, a lot of the things that we talk about at the time were sort of from the perspective of Western astronomers and also Northern Hemisphere astronomers. So if you look at the collection of 88 constellations now, for example, the sort of 48 of them, or 47 if you exclude Argo Navis, that are still included in it were all or mostly constellations that you can spot in the Northern Hemisphere. Some of them you can obviously spot in the Southern Hemisphere as well. But the Southern Hemisphere only constellations are all completely different. They're not the same. They're different things, and they're not based as much in ancient Greek mythology. So there might have been some things that he was able to spot. Generally, the ones you see in the maps are Northern Hemisphere constellations only. Yeah.
Because Canopus was there, that great,
Mm-hmm.
in the big boat one.
Yeah.
And that's actually quite far south. You can
Yes.
get that from London, for
Yeah, that's a good question. I don't actually know for sure if he did have any input from anywhere else or if he traveled anywhere else. I know most of his work was based at the observatory. But stars like Sirius and in that those constellations, you're not always able to see them all year round in the Northern Hemisphere. Sometimes it's only sort of times of year. So there are certain constellations you can only see in the wintertime, others you can only see in the summertime. So it might have been a bit of that, but maybe he did have other input. I don't actually know for sure. Mhm.
Thank you very much. On the topic of the solar activities, of course, we're aware that once there is more activity, we have these beautiful northern lights. But other than that, are we aware of any other events that happen across the globe, such as natural disasters or anything that it might be linked to?
That's a really good question. The answer is sort of not really. There's been a lot of discussion about with climate change and global warming, if the cycle of the sun has anything to sort of do with that. And we don't know 100% for sure, but generally the consensus is sort of no, not really. And that's because the sun, as far as we're aware and as far as data shows, has been going through this cycle pretty consistently for hundreds of years. And there being a maximum of sunspots doesn't really affect anything that much. Annie Maunder and Edward Maunder also have a sort of fun period of time named after them called the Maunder minimum, which is they looked at some data from the 1600s and 1700s where there was a suspiciously low amount of recorded sunspots on the sun for a pretty significant chunk of time. It doesn't follow the trend at all. That's now named the Maunder minimum. I don't know all of the science behind it, but there wasn't anything sort of catastrophic or any sort of major events on Earth that would have sort of correlated with that. That shows that there's any sort of major disruptions caused by the presence or not of sunspots. If that makes sense. I hope that helps.
The graph that you showed, was that kind of showing a decrease in solar activity? Sunspot.
This graph?
Yeah, it seems to be decreasing over time.
Yeah, you're right. So this graph is, I guess its sort of aim is to show that between 1994 and 2000, there's a period where there's not very many sunset spots. There's lots and lots, and then there's not. This graph sort of ends in 2019. Actually goes on to 2024, but it doesn't look like anyone's put much data on it. So I think overall it's showing a pretty consistent trend. This is not a full set of up-to-date data. So it wouldn't surprise me that if you added it, this part here at the minimum would then end up expanding out into another nice butterfly. And as with all sort of data, there's always lots of sporadic outliers that you can see all over. So we're in what scientists call at the moment solar cycle 25. So I haven't heard any news to say that anything out of the ordinary is occurring. So I think what this is actually a slightly incomplete set of data that will get filled as sort of the years go on. Does that make sense? Amazing.
Yeah. You were saying about the new plans that you have, well, all of you guys
Yeah.
have at the observatory. Are there any projects of collaboration with other maybe not observatories, but with other astronomical centers in the UK?
Yeah, so this is something that we have a team that does do, and something that the project sort of aims to do is increase collaboration with sort of not only different places but also different communities. So the observatory at the moment runs programs with an example that comes to my head immediately is we run an Astronomy and Islam program, which looks at the links between the Muslim calendar and ancient sort of Islamic astronomers that looked sort of at stars. And we did a sort of whole program around that. That was one example, and it worked very successfully at, engaging the local community. So I think there's lots of desire to work with other sort of local communities and things like that to maybe sort of co-create and bring in different communities and different cultures and try and sort of find out their thing, or what they know and what they believe and what they look at with space. Because as I say, what we know is a very sort of Eurocentric, observatory-centric perspective of astronomy. So I think it would be really nice to sort of get different voices and different opinions and work with other people from different science centers who maybe have more experience with that to try and sort of collaborate and put something like that together. Yeah, thank you.
Hi, I wanted to know what the y-axis was.
Yeah, the y-axis is latitude, so how far north or south the sunspots are from the equator. So with the sun, this sort of yellow section, I probably should have made it clearer, is a sort of representation of the face of the sun. So it sort of helps you imagine the position of the sunspots on the face of the sun, with this line here in the middle being 0 degrees latitude, essentially the equator. Does that help?
So yeah, so when it's know that it goes up and down in terms of intensity or frequency, does that mean the further away the greater amount of sunspots there are?
That's a good question. So something else that sunspots sort of appear to do over time is move a little bit. They don't always sort of stay in the same spot on the sun, or more will appear in sort of different places. So obviously this is a static graph, so it doesn't fully capture the fact that sunspots move, and at different times you tend to get them at higher latitudes versus lower latitudes closer to the equator. I don't know if that's answered your question, but yes, I think generally when you have more sunspots, you end up with sort of more all over the place.
No, I can't see it. I can't see the higher intensity. Like,
so if we take 2014, which is just here, around here, it's much more densely packed with sunspots, but you do also get sort of strays further down, whereas at sort of periods of minimum, they end up sort of further away from the equator, and then more sort of appear getting closer and closer towards the equator as the years goes on. That's essentially just sort of what the data's showing.
Oh, hello. We've reached the end. I've got one final question online, which I thought was probably a nice one to end on, which is, what do you think the Greenwich Observatory site will be used for in another 350 years?
That is a good question. That's a really, really good question. Well, 350 years is, as I say, it's a really long time. So when we think about, I guess, maybe some of the bigger things that have happened in the world of space and space exploration in 350 years, for me, one of the biggest things that comes to mind is human beings having been into space, been on the moon. And, there's lots and lots of talk at the moment about sending human beings further into space in 350 years, given how sort of those current plans seem to be within our lifetimes. In 350 years, you like to think that maybe us human beings have managed to get even further out into space. In terms of the observatory itself and the work that it does, sort of more focusing on observing and astronomy, one of the things that's always pretty reliable is Halley's Comet. That will come back. The observatory likes to make a big thing of that. that will probably still be happening in 350 years if people stay consistent. A lot of things in the universe are sort of pretty consistent in that we know they'll happen time and time and again, right? So even if the technology that we look at them with changes or our ability to see them improves, things like solar eclipses or lunar eclipses that we study or look at from the observatory, you like to think that we, you know, still be doing that and still talking to members of the public and school children and things like that about that, even if it's with slightly improved tech. It's probably what I would estimate.
Well, thank you very much.
Thank you.
If we give our speaker another big round of applause.